So in this exercise, we're basically just simplifying a resistive network. So what they're asking us here is to simplify this circuit by reducing all these resistances into one equivalent resistance. And they're looking at this across AB, so it's looking back into the circuit this way. So that basically means, if we were to disconnect this voltage source here and put an ohm meter across AB, what resistance would we measure? So this is just applying series and parallel resistance relationships to come up with equivalent resistance. So let's look at how this would work. So the first ones we want to look at are these resistors here, 2, 4, and 6, and we see that they are just in series. So when they're in series, we just add them together. So that being the case, that'll just be 6 plus 4 plus 2. Of course, that gives us 12 ohms. So those three resistors right there can be replaced by a 12 ohm resistor. So let's do that really quick. So if we eliminate all of this here, and we can come back and replace that with one 12 ohm resistor. And so what that will look like then is if we come back here and we put a new resistor here of 12 ohms. Okay, so we've reduced it some already. So now we look at our circuit and we see that this 12 ohm and 10 ohm resistor are in parallel. So to get an equivalent resistance of that, we can apply our parallel resistance relationship. And so that's going to be the 10 ohm times the 12 ohm over 10 plus 12 ohms. And so when you have two resistors in parallel, that's the relationship for those. And when we calculate this out, put it in the calculator, that's 5.45 ohms. So that being the case, these two resistors here can then be replaced by one resistor. So to do that, this guy right here will be gone altogether. And then, get this a little bigger. So that's will all be gone. And we're replaced then with 5.45 ohms right there. Okay, so we're getting closer. So now we see that this resistance and this resistance are in parallel. So when in series. So when resistors are in series, we just add them. So that'll be 5 plus 5.45. So that gives us 10.45. So those two resistors can be replaced by one resistor with a value of 10.45. So that being the case, we will eliminate one of those, and we're left with this one. So we can complete that. And then this will be a resistance of 10.45 ohms. All right. So now we see, if we look at this closely, these three resistors here are actually in parallel. All three show the same input here and the same output there. So when we have resistances in parallel, we have an equation or relationship of how we can relate those. So we're going to call this new resistor RE. So this will be our equivalent resistance. And so to get that, we know that if we have three resistors in parallel, our total is going to be 1 over R1 plus 1 over R2 plus 1 over R3. So in our case, we'll do that. Our total will be our equivalent resistance. And so then that'll be 1 over 10.45 plus 1 over 7 plus 1 over 6. And we plug that in the calculator and calculate it out, and we end up with a number of about 0.41. But this isn't our answer. The answer is we have to take the reciprocal of that. So that means that RE is going to be equal to 1 over 0.41, which if we plug that in the calculator, we will get about 2.47 ohms. So that means then that all these resistances go away except for one. So we'll take all these out, those three in parallel. And our new resistance here is going to simply be 2.47 ohms. So that entire network that we saw could be replaced by one 2.47 ohm resistor. So now we're asked one other question as a part of this exercise. What is the power supplied by the 12-volt source? Well, we recall our power equation. P is equal to the voltage times the current. But we can rewrite that because remember Ohm's law says that the current can be equal to the voltage over the resistance. So if we substitute this VR in place of that I, then we will get V squared over R. So in this case, it's 12 squared over 2.47. We calculate that out, it's 58.3 watts. So that's the power supplied by the source.